Okay, welcome back everybody. Today we're going to actually use the Feynman path integral to obtain a few very interesting results and physical phenomena. And in the first video today, we're going to actually derive a very unexpected, surprising result. Namely, we're going to see how the Newton equation, second Newton law of classical physics, appears in the so-called classical limit of the Feynman path integral. So more precisely, what I'm gonna do, I'm gonna start with the with an expression that we discussed in the previous lecture. So which tells us that the probability of a quantum particle to go from an initial point r sub I to a finite point r sub f can be written as the sum, absolute value of a sum over all classical trajectories, which sort of symbolically represents what we call the path integral of these individual quantum mechanical transition amplitudes. And each of these amplitudes is written as the exponential of this imaginary constant I times the classical action divided by the Planck constant. And surprisingly, what we're going to see is that the familiar equations of motion of the classical physics, the Newton's second law, appears as a result of taking the classical limit in this expression. And I'm going to formulate precisely what I mean by the classical limit, but at this stage let me just tell you that the classical limit will imply suppressing the essence of quantum mechanics, the interference phenomena, which are controlled by this Planck constant h bar. Now, just as a side comment here, sort of a historical comment, let me mention something about this equation. So, of course, this is, I expect all of you, or the majority of you, to know this equation. It's something we learn oftentimes in high school, which is the second Newton law, that mass times acceleration of a classical particle is equal to the sum of all the forces acting on the particle. So, apparently, if you read actually the original scientific work by Newton, the first version, the first edition of this Principia was published back in 1687, a long time ago. So we are not actually going to see this equation in this modern form. The closest formulation to what we currently call Newton's second law of motion appeared in his original work in the following form. A change in motion is proportional to the motive force impressed and takes place along the straight line in which that force is impressed. It probably requires some imagination to connect this statement to to this equation, but in any case, obviously Newton not only understood the basic principles of classical mechanics, he was the one who created it. So there's no question about that. So this comment I just wanted to make to show you that sometimes the original discoveries evolve very strongly from their original form and become, even though we still give credit to people who were the first to put them together, the final form may be quite different from what they were envisioning. And this is a perfect example of that. Now, going back to the main subject of this video, so now I'm going to actually show you how mathematically this old and well-known second Newton law appears from this modern, more sophisticated quantum theory, seemingly unrelated theory. So in order for me to show you how it happens, I need to present a mathematical trick or method called Laplace's method or saddle point approximation, which allows us to calculate certain integrals that otherwise cannot be calculated analytically. And this method, as we will see, sort of propagates to more complicated theories, including our ability to calculate certain path integrals approximately. Now, we have seen already the Gaussian integral, which is an integral of e to the power minus x squared, and between minus infinity to plus infinity, and we know the result is equal to the square root of pi. So, of course, what this integral is the area enclosed by this curve, which is nothing but the plot of this Gaussian function, e minus x squared as a function of x. Now, of course, this function is special. Well, there is nothing particularly special about this function, but it does appear in many fields of math and physics. And one property of this function is that it decays very, very fast. when the argument x becomes large, either very negative or very positive. Now, in general, however, if we want to calculate the integral of, let's say, from minus infinity to plus infinity, or some other limits of a function e to the power minus f of x, where f of x is a relatively arbitrary function, there is no closed mathematical expression typically for such an integral. But it turns out that if there is a small parameter in the exponential, if this function actually involves not just f of x, but f of x divided by some epsilon, and this epsilon is very small, then one in many cases can simplify things. And I will explain the logic behind this simplification on a particular example of this function f of x, which is x squared plus 1 over x squared. And so I want to integrate the exponential of minus this function from minus infinity to plus infinity. So there is no closed analytical expression for the integral of this sort, but it turns out that if indeed we have this small parameter in the denominator of the exponential, things can actually be simplified. In order to see how it happens, let me plot this function f of x. So if we do so, we see that there is a minimum, but of course, due to the minus sign in the exponential, the smaller the f of x, the larger the exponential itself, and vice versa. So if f of x, on the other hand, becomes very large and positive, e to the power minus f of x becomes negligible. So if we now plot the function that we actually want to integrate, it's going to look approximately like this. So it's my artistic expression of what it's going to look like. But the point here is that it will have a maximum around where f of x is minimal, and it's going to have these tails which become smaller and smaller as f of x becomes larger. And so what we want, of course, geometrically, we want to collect the area enclosed by this curve. And so some area will come from the region of this maximum, some area will come from these tails. So, but as epsilon, this parameter here becomes smaller and smaller, let's say when it's 0.1 or something like that, so then it implies that I will exponentiate e to the power 1 over 0.1, which means e to the power 10 of whatever these tails are, and so these tails will become less and less relevant on the background of this peak. So for instance, for a smaller epsilon, so let's say my f of x for a smaller epsilon is going to look like this. So, and in some sense, it's going to become closer and closer to the Gaussian form. So the reason for that is because if I expand my function f of x in Taylor series in the vicinity of this point f of x equals 1, so what I'm going to get so is the first term, which is just the value of my function at f at x equal 1, plus f prime of f equals 1, x minus 1, plus f 2 primes divided by 2, x minus 1 squared. But since this is the minimum of my function, so the derivative, the first derivative of my function here vanishes, so it becomes equal to 0. And so the only terms which are sort of in the leading order that matter are this guy and the quadratic term. So essentially, which makes the integral that I'm dealing with Gaussian. And as I mentioned, we know how to calculate Gaussian integrals. So without going through the algebra, let me just sort of present the result. So here I first present sort of a general result for almost arbitrary function f of x, and the first factor here comes essentially from just simply calculating the value of this exponential in the minimum point of f, and the second term is the result of integrating the Gaussian part, much like this Gaussian integral. So for the particular function that we consider, well, we are not going to need this result at all. So it was just an example, but nevertheless, here is the answer. Let me also mention another fact, which I'm not going to prove it, but it's important for the following, that even if we have a slightly different integral, when we have an exponential of I, the imaginary constant I, over some small parameter and some f of x, so this integral oftentimes too can be simplified using this very similar saddle point approximation, what we just discussed. And the reason for that is because e to the power I f of x can be written as a bunch of cosines and sines, And if epsilon becomes very small, they become strongly oscillating functions, which on the average give us 0 if epsilon is small, because you have a plus, a positive part of the cosine, a negative part of the cosine, and then in some sense balance each other out and give on the average 0. And there is a similar argument that you can actually write the expression of this integral in a very similar form and focus only on the minimum of this function. Now let me go back to quantum physics, and we're going to see how the previous mathematical discussion is going to become relevant. Now remember, so my motivation in the very beginning, I said that I want to take the classical limit of my quantum mechanical theory. So what does it mean to take a classical limit? So let us recall that the most interesting quantum phenomenon, the way how quantum mechanics was actually discovered, implied interference between different waves, sort of describing wave functions describing a particle. So if we want to kill, in some sense, the quantum mechanical effects, we want to suppress the interference phenomena, or we want to make the wavelength as small as possible. So let's say if we have a particle with a momentum p, so the corresponding wavelength is going to be, per de Broglie's argument, is going to be h bar over 2 pi p. So if we want to set a lambda to 0, that is to completely suppress the interference effects of the particle with such a wavelength, we want to set, in some sense, h to 0. So the Planck constant, which controls the quantum effects, which is sort of the essence of quantum mechanics, so it should be set to 0 in order to take. So now, if we recall the expression for the Feynman path integral, so we see that in the quasi-classical limit, when h formally is taken to 0, the function that we are actually, or functional better to say, that we're integrating, becomes in some sense very similar to the types of functions that we saw in the previous slide, with the h bar here, the Planck constant, being equivalent in a sense with the to the epsilon, parameter epsilon, that control the applicability of the saddle point approximation. And also in the full analogy with this previous slide, with the saddle point approximation, we can say that as h becomes smaller and smaller, so we can only focus on the trajectories in the vicinity of the trajectory for which the action is minimal. So basically the limit of h going to 0 therefore reproduces the principle of least action, which is another sort of cornerstone of classical physics. Now, I should comment here that, of course, h bar, the Planck constant, is a fundamental physics constant. We cannot take it to 0. We cannot take the limit physically of h bar going to 0. What it actually means when I'm saying that h bar goes to 0, and this is also, you're going to see it in textbooks on quasi-classical approximation, it means that we have essentially two types of length scales in our problem. One type of length scale is the wavelengths of our quantum particles. And the other type of length scales is the typical length scales in our system. And if the wavelength of our quantum particles are much smaller than everything else, this effectively means this limit, and this effectively means the applicability of the quasi-classical approximation. So for those of you familiar with the Lagrangian classical mechanics, it should be clear now that principle of least action already demands that we essentially are going to reproduce Newton's equations as was advertised in the beginning of the lecture. So you can stop listening to the lecture right here and move on to the next part. But for the sake of completeness, let me nevertheless present or remind you how these equations would come about. So again, how the question that we're now asking, okay, we have found that, well, if we take the Planck constant to 0, or if we consider the wavelengths which are much smaller than everything else, we essentially we must extract the minimum of the classical action from the path integral. And this minimum would occur on a particular trajectory that particle will follow. So how to find this special trajectory? So we can sort of motivate the standard, what is known as variational analysis, by this, again, simple analogy using the usual functions. So suppose we have an arbitrary function f of x, which has a minimum, or maximum in principle too, somewhere, but let's assume it's a minimum, and we want to determine the point where this minimum actually occurs. And for this, I can again use the Taylor expansion for the wave function in the for this function f in the vicinity of this point x0 that I'm trying to find. And so it's going to have the value of the function at x naught, the first derivative, the second derivative, etc. And the minimum of this function, so if I have a function, so this minimum is going to occur where this derivative, where the tangent to this plot f of x as a function of x is going to be horizontal to the x direction, or the first derivative vanishes. Now, in analogy to this, if we have now a functional, or in particular our action s of x, so to determine a particular trajectory, which we will identify as a classical trajectory, so we have to demand that if we calculate this action in the vicinity of this classical trajectory, for which the action is minimal, the first sort of variation, the analogy, well, the analogous part to this first derivative is going to vanish. And this symbol, delta s equals 0, so this equation is a sort of mathematical expression for this principle of the least action, and in some sense all of classical physics is contained in this equation, which is actually quite remarkable. Now, if we now go back to, well, and recall the particular action we're studying now, which is just the kinetic energy mv squared over 2 minus the potential energy for a certain quantum particle. So in order to find the classical trajectory, as we know, we want to calculate the first variation, and we do so by writing this action in the vicinity of the classical trajectory that we want to find. So in some sense, what we should think about is that we have this initial point and we have this final point, and there is some unique trajectory that we're looking for, but there are also trajectory very close to it. And this deviation from this, so this black trajectory here is the classical trajectory, and the red ones are this r classical plus dr. This dr is a small deviation from the classical path. So if we now just simply plug this expression into this expression for the action, so we're going to have the kinetic energy term. So of course the velocity is just dr over dt, or for brevity we can write it as r dot. So we're going to have here the two terms, and we're going to have two terms as an argument of the potential energy. And since dr is very small, we're going to keep track only of the linear terms here. So for example, in the kinetic energy part, so here we're going to have m over 2 classical velocity squared plus the linear term, which comes from 2r dot dr. So we're going to have m r classical dot plus dr dot. And this guy, what we're going to do, we're going to expand this function in Taylor series up to linear order. And again, we can do that because this dr is very small. And so we're going to have the classical, v of r classical minus dv over dr, the gradient, dot dr. And everything integrated over time. So we have four terms here. So this term is simple enough. And these two terms, actually, this guy and this guy, together they represent the classical action. So the one which occurs on the classical trajectory. Remember, what we want is not the classical action itself, but in some sense the derivative of the action, basically something which is proportional to this dr. So the only term which is sort of non-trivial is this guy, okay, and it can be further simplified by using the integration by parts. So just to remind you, I'm sure you have, many of you have seen it before. So if we have an integral, let's say from a to b of a function f times g prime dx, so we can write it as the derivative of everything f g prime minus f prime g. And so here I have the full derivative, and I can basically calculate the value of the functions at the limits, and essentially move the derivative from the function g to the function f. Now in our case, the role of the function g is played by this dr dot, and the role of the function f is played by this mr dot. So we want to move the derivative over time from here to here. But this full derivative term, so if we're going to calculate the values of this function dr in the endpoints at time 0 and at time t, they correspond to the endpoints of this trajectory. So, and our trajectory, remember, is pinned. So we have to go from the prescribed initial point to a prescribed final point. So there is no freedom for this sort of fluctuation to deviate from these initial and final points. It can only deviate from the classical trajectory in between. So what I'm saying here is that this term, the full derivative term in this particular case vanishes, and we can simply move the derivative from here to here with a minus sign. So if we put everything together based on this discussion, so essentially if we integrate by parts and replace this and this term with the classical action, we're going to have this classical action minus, because there is going to be minus here and there is already a minus here, integral from 0 to r, r2 dots, second derivative, because we moved it, plus dv over dr, and everything is multiplied by this this thing, delta r. Now, and remember, this is exactly our first variation, and this is something we want to set to 0. And this guy must be equal to 0 for every possible sort of fluctuation away from the classical trajectory. And this implies that this expression in the curly brackets, so this expression must be identically equal to 0 for the first variation to vanish, for us to be able to find the minimum of the action. And if we're actually going to write it, we're going to get mr2 dots is equal to minus dv over dr. Well, the second derivative of the coordinate is known as the acceleration, so the left-hand side is simply m times a, and the right-hand side is the gradient of the potential energy, which is the force acting on the particle. So we see that we indeed have derived the Newton's second law from the principle of the action being minimal. And this principle itself followed from us taking the formal limit of h bar going to 0, from setting to 0 the wavelengths of our particles.